All right, we're going to move to chapter 21 in your textbook. Just to give an update, I've gone in and added a few Learn Smarts for your reading. I'm not going to require those anymore as far as a grade, and I'll make an announcement on email in more detail. But at any rate, these are going to be supplemental, so it's just for further reading. But anyway, we are at chapter 21, and what we're going to be getting into now is a different reaction profile that we're going to see with the carbonyl containing compounds. So let's just recap where we are. So thus far we've seen what we call nucleophilic addition. Right, this will be where we look at a compound such as a ketone, and we add a nucleophile to the carbonyl. So what we've done here is we've added the nucleophile to the carbonyl, so this is just simply nucleophilic addition. The other reaction that we saw with carbonyl containing compounds, specifically in the carboxylic acid derivatives, was nucleophilic addition elimination, or what's also called nucleophilic acyl substitution, but I prefer the nucleophilic addition elimination term. So if we look at something like an ester, all right, and we react this with ammonia, for example, which would be a nucleophile, what we're going to do is we're going to add the nitrogen and eliminate the oxygen. All right, so that was covered in our last set of videos. So what we're doing here is we're adding nitrogen and removing oxygen here. So the OR group is eliminated, thus the elimination term, and the nitrogen atom and its two hydrogens are added, thus the addition term. So now what we're going to look at is a new subset of these reactions, or a new class of reactions. And these are going to be called reactions at the alpha carbon. And I'm going to use the Greek letter alpha to symbolize this from now on. All right, so we kind of need to go back and define what an alpha carbon is, especially in when talking about a carbonyl containing compound. So if I take a look at a ketone like this, all right, so what I have is an R group on one side of the ketone and an R group on the other side of the ketone, but what I want to focus on here is this carbon that is adjacent to the carbonyl on the ketone, and this is the so-called alpha carbon, all right? So it is the carbon that is directly attached to the carbonyl carbon, and it's called the alpha carbon, all right? It's a special carbon because we can perform reactions at this position that we ordinarily couldn't do without a carbonyl. All right, so the carbonyl makes this alpha carbon very special. So how is it special? Well, the fact that it's acidic in a protonated, that it's acidic due to it being adjacent to the carbonyl. So what am I talking about? Let me draw this out. It's a little bit easier to visualize than it is to define. So if I have two protons there, all right, what I can do is I can tautomerize this compound into something called an enol, especially if I'm an acid, all right? We've talked about this in the past, but we're going to go ahead and recap here. If I'm an acid, what I can do is I can protonate the carbonyl. We've seen this before, and this is a reversible process. Now I have water. And the water will actually attack one of the hydrogens at this alpha position that I've just marked here. All right. And the reason why is that we can delocalize the electrons onto oxygen to mitigate that positive charge. So what this does is effectively give us a tautomer of the original ketone. And a tautomer, by definition, is an isomer, right? They have the same chemical formula, but they differ by the position of their pi bond and a proton. So in the keto form, what we call here, the ketone or the keto form, we see where the double bond, or the pi bond, is between an oxygen and a carbon, and we have two hydrogens at the alpha position. Over here on the enol, now our pi bond is between two carbons, and our hydrogen has moved from a carbon-hydrogen bond to an oxygen-hydrogen bond. So we have this, what is called tautomerization. So to recap how this works, in acid, we have our keto form, and if this is an acid, we can tautomerize to the enol form. All right. So the word enol, all right, it's an alcohol because of the OH group, but that OH group is directly attached to a CC double bond, or what we call an ene. So it is literally just formed from ene and all put together, so we get enol. All right. So how will we visualize how this changes? All right. So what ends up happening here is the single bond framework all stays the same. All right, so if you notice, all the single bonds stay the same. The only thing that changes is the double bond moves from the CO to the CC. And the CC that we're going to make is what was the carbonyl carbon to the alpha carbon now. All right, and in order to do that, a hydrogen had to get out of town and move up to the oxygen. So that's how we rationalize drawing the keto to the enol form. All right. So what is, the purpose of this? Well, to be honest, in acid, typically what we're going to see is about 99% of the tautomers are going to be in the keto form, where we have about 1% in the enol form. All right. So if you put a ketone in acid that can form an enol, you're going to expect about 1% of it to form that enol. All right, and there's other factors at play. The nature of the R groups can really change this ratio, but for the most part, we're just going to go ahead and say that it mostly exists in the keto form. Well, so what's the point of studying this? Well, it turns out that the enol is what we call nucleophilic. All right. That's cool, because the keto we saw earlier, we were adding nucleophiles to the ketones, right? So they were electrophiles. But you can change a ketone, which is electrophilic, into a nucleophilic compound called an enol. So that allows us to add electrophiles to enols. So how does this work? Well, we're going to look at nucleophilic addition. By enols. All right, so how are enols going to be nucleophiles? All right, so what I want to do is I want to take a look at this ketone first. I'm going to put it in acid. This is precisely what we did on the previous slide. So it's going to what we call enolize, which means it makes the enol. So I draw my single bond framework, change the position of the double bond, and move the hydrogen up onto the oxygen. So now I have the enol. And if the enol is in the presence of an electrophile, I'll call this E+, the the enol will actually react with this electrophile. And the way this works is it'll reform the double bond between the oxygen and the carbon, and the CC double bond will then go out and attack the electrophile. All right. So what we're going to end up doing is following the alpha carbon here. All right. The alpha carbon is that carbon that was adjacent to the carbonyl, and now in the enol form, it's where I've marked it. This is where the electrophile actually adds. In the alpha position. So that's pretty cool. If you can form the enol, right, remember, it's about 99:1 ratio, so the ketone dominates, but every time you form the enol, it reacts. So what ends up happening here is we have an irreversible second step, and eventually, every time you form the enol, it reacts, thus it shifts the equilibrium all the way to the products, and we get nice clean addition by enols, all right, to the alpha carbon. So what we're having here is electrophilic addition to the alpha carbon. All right, and we can do that with enols. All right. So what I want to recap here is if you have a ketone and you put it in acid, you can form an enol. All right. But what happens if we take the same ketone and put it in base? Well, we're going to get a different type of tautomerization here. So now, if I put this in base, and I'm just going to put B- here as a generic base, I can actually pull this proton off here and shift the placement of the double bond. I'm going to draw the alpha being there, and I've got BH now. All right. So what we're doing here is we're directly forming something that looks a lot like the enol, all right? And we've actually formed something called its conjugate base that is known as the enolate. All right? So 8 often indicates that you're dealing with a conjugate base, like a carboxylate. Here we have an enolate. So it's the conjugate base of the enol, right? And they turn out to be much, much more nucleophilic than their enol conjugate acids, all right? So enolates are far more reactive, and so it's a good idea to learn how to use them since they're so reactive, all right? You can make enolates out of different compounds other than ketones. All right, so let's just kind of recap here. Could I take a ketone called benzophenone and make an enol or an enolate? So the question is this enolizable? All right, could I make an enol or an enolate? And the answer is no. All right, the reason why is because if we look at the two alpha positions, neither of them have a hydrogen, all right? So we can't shift the hydrogen from the alpha because there isn't a hydrogen at the alpha, all right? So the answer is this is not enolizable. What about acetophenone? Is this enolizable? All right, we take a look at the two alpha positions, and the answer is yes, all right? This alpha does not have a proton at the alpha position. However, this one does. All right, we actually have 3 hydrogens there that are enolizable. All right, so we could enolize acetophenone, but not benzophenone. All right, so let's take a look at perhaps an ester. All right, let's look at ethyl acetate. I'm going to draw it a little bit differently. All right, so this is the molecule ethyl acetate. And it does contain a carbonyl. So my question now is this enolizable? All right. So where are the alpha positions? Right, they're adjacent to the carbonyl. So in fact, here oxygen is the alpha position, and it does not contain a hydrogen. So this is a no, right? But what about over here? That alpha position, yeah, that checks out. All right. We now have hydrogens at that alpha position. So ethyl acetate indeed is enolizable. So the question now is it more or less enolizable than a ketone? And we'll get to that by looking at table 21.2 in your textbook. All right. So when we look at that table, what that's going to do is it's going to give values of pKa values for a variety of acids. All right. So how are we going to use this to decide whether something is more or less enolizable than another compound? Oops. Let's take a look here. First one I'm going to draw is a ketone. All right. So I'm going to look at this ketone here. And what I'm going to do is I'm going to put what we call acidic hydrogen in red there. All right. So that's the hydrogen that we would remove with the base. Recall it's at the alpha position. All right. So if I can remove that hydrogen with the base, well, that's an acidic hydrogen that I've just highlighted there in red. So if it's an acidic hydrogen, that means it also has a pKa value associated with it. And generally, we think of ketones having pKa values around 19. All right. So it's less acidic than water. All right. But it's, somewhat acidic for a carbon acid. All right. So you don't typically see too many carbon acids, and this just happens to be one of them. All right. So what are some other carboxylic acid derivatives that could be acidic? Let's take a look at the ester in ethyl acetate. So I'm going to highlight that in there. All right. So the acidic hydrogen on ethyl acetate I've highlighted in blue. All right. It's attached to the alpha carbon. Turns out that the pKa value for an ester is about 25. All right. And again, this appears in your table 21.2 in your textbook. So my question now is, which one is more basic? All right. Pardon me. Which one is more acidic? All right. So what that means is that the ketone here is more acidic. And how do I know that? Of course, the lower the pKa value, the more acidic the compound is. All right. And this guy is less acidic. Okay. Higher pKa value, less acidic. So remember, if you have a compound that is more acidic, what does that mean for its conjugate base? That means it has a more stable conjugate base. All right, what am I trying to say here? Look at the ketone and look at the ethyl acetate, the ester. Which one's more acidic? Well, we have the pKa value that tells us that what? The ketone is more acidic, thus it's going to have a more stable conjugate base. What does that mean? It's easier to form. All right, and what is the conjugate base of this ketone? Well, it's an enolate. All right, so what we're going to say here is that the more acidic a alpha hydrogen is, the easier it is to make an enolate. All right. So let's take a look at the ketone again. All right. And if I take a base what is the enolate that I make? All right, so recall, here's my alpha position. I'm going to remove the hydrogen from the alpha and put a double bond between the alpha carbon and the carbonyl carbon, and remove the double bond from the carbon-oxygen bond. All right, so what I get here is the following. Oops, messy double bond there. Man, I'm having trouble with this. Start over. All right, let's try this again. Double bond. All right, cool. So there is my enolate. All right. So ketone on the left, enolate on the right. That's easy to form relative to what? The ester. What do we have on the ester ethylacetate? So here's the alpha position. If I treat this with base, put in my lone pairs. There, I've made the enolate of the ester, or what's called the enolate anion equivalent. All right, that's just being fancy. We can just call it an enolate of an ester. It's totally fine. So which one's easier to form? All right, here, easier to form. Why? Because the ketone, alpha hydrogen, is more acidic. Thus, it is easier to form its enolate. All right, that's a key point. So when I take two new molecules that you've never seen before, and I'm going to ask you which one's easier to form its enolate. Let's see if we can get that. All right, I'm going to take a look at, let's do an aldehyde this time. Now be careful. Which one is the acidic hydrogen in the aldehyde? All right, in order to do that, you need to find the alpha position there and there. All right, so this is where it gets confusing. The alpha carbon must contain a hydrogen. All right, so over here this isn't even applicable, right? Because that's not an alpha carbon. That's a what? That's a hydrogen attached to the carbonyl at the alpha position. So that's not what we would call an alpha hydrogen, right? It's a bit strange in aldehydes, right? This is what we call the formyl hydrogen. And for our purposes, it is not acidic, all right? So over here, this is the acidic alpha hydrogen, all right? So it has a pKa value of 17, all right? So relatively low number. And let's take a look at an amide. All right, and we're going to take a look at that alpha hydrogen, and the pKa value of an amide is around 30. All right, okay, which one is more enolizable? The answer to your question should go as following. Which one's more acidic? Right? The aldehyde. If it's more acidic, it also means more enolizable. There's an E over there, I promise. All right, so it's more enolizable. So the amide is less enolizable. In fact, it's the least enolizable that we've seen thus far. All right, let's take a look at the pKa's of these acids. 30 for the amide, 25 for the ester, 19 for the ketone, and 17 for the aldehyde. So the aldehyde is actually the most enolizable that we've seen thus far, and the amide is the least enolizable. And I'm not going to go through every single enolizable compound there is. That's why I'm pointing you towards table 21.2. What you're going to see there is a list of pKa values, and it's going to tell you how to enolize these things. All right. or how easily they can be enolized. Now, what I want to talk about next is, all right, well, what kind of bases are we going to use? All right, so what we're going to look at first is what bases work. And this is where mastering the idea of pKa's and equilibrium becomes quite important. All right, so let's go ahead and take a look at a ketone again. And we're going to put a base here. And we're going to draw the equilibrium for this reaction. All right, so we have a base and we have a ketone that is enolizable. And we're going to go ahead and draw that enolate that results. And the conjugate acid of our base B minus. All right. So what we need to do now is figure out, well, which side does the equilibrium lie? All right. If it lies to the left, what does that mean? That means our base is not going to work very well for this reaction. If the equilibrium lies towards the products or the right, that means our base was very effective at driving this reaction to completion. So how do we determine which one's which? It comes down to pKa values. All right. So the idea here is that equilibrium prefers formation of the weaker base. All right. So what you're going to want to do is identify the pKa's of the two acids in this equation. All right. On the left, what is our acid? Well, it's clearly not B minus. That's our base. All right. It's what gave up the hydrogen. So our acid is the ketone. And we said earlier that the pKa value of this guy is around 19. Where's the acid on our product side? Well, it's going to be BH. All right. BH is our acid. Well, what's the pKa of that? Well, it's impossible to know because we don't know what the heck B is. All right. But what would you want it to be for the reaction to go all the way to the right? Okay. Well, equilibrium prefers formation of the weaker base. This is also true if you say and the weaker acid. You say, well, how can that both be true? Well, strong acids want to give away their protons, all right? So they want to get to their conjugate base form. So strong acids, they're hard to form, all right, in equilibrium. So there's just like a weaker base. If a base is very strong, it's going to want to grab that proton and move. So when you find that you're at a weak acid or a weak base, you've gotten to a chill spot, all right? So in order for this to work effectively, what should our pKa value of BH be, all right? Should it be higher than 19 or lower than 19? Well, again, we're trying to form what? The weaker acid, all right? So in order for BH to be weaker, the pKa value must be larger than 19, all right? So what we're going to do is we're going to draw the alligator mouth eating the pKa value that we have no idea what it is. But if we're going to claim that we want this reaction to work very effectively, we're going to need our pKa value to be greater than 19, all right? Greater than 19. If it was right at 19, what would you say? The equilibrium would be what? Right down the middle, okay? If it was a pKa value for BH at 18, what would you say? It's going to be more on the left, all right? What if it was 17, even more on the left? What if BH pKa was 0? Yeah, that thing's all the way to the left. It's not going to happen, all right? So we need to figure out what is a good BH here, all right? So let's redraw this. All right, there's our equilibrium. So on the left, we have an acid with a pKa of around 19. So BH, we want to be 19 or higher for this thing to really get going. All right, but let's look at a couple bases here. All right, so let's take a look at B minus being equal to something called sodium hydroxide. All right, now I drew sodium there because that's the formulation that you typically will see hydroxide ion coming from. All right, it's all about the hydroxide ion. It doesn't matter if it's sodium or lithium for the most part. So I can actually just go ahead and get rid of the sodium. All right, if it was lithium hydroxide, potassium hydroxide, it would roughly be the same effect. All right. So what's the pKa value of hydroxide? Well, that's an irrelevant question because hydroxide is actually a base. Oh, so how are we going to figure this out? All right. Well, we're looking at B minus. All right. BH, that's what's important. The pKa of BH is what's important. All right. So here, the pKa of BH, which would be what? Water, right? Pardon me. Let me back this up a little bit. So BH would be equal to what? Water. All right. How do I know that? Well, B minus is what? OH minus. I add a proton to it, it becomes H2O. So BH, the pKa, is 17. All right. Depending on your textbook, it could be a little bit higher or lower, but 17 is a good value for the pKa of water. All right. So is that going to work? All right, for our equilibrium up there. Well, 17 is less than 19, so water is actually less acidic than the ketone, but it works a little bit, right? So what we're going to say here is percent enolate. Move that up. The percent enolate would be less than 1%. All right, so you're going to make just a little bit of enolate. But remember, when we saw reactions earlier, if you make just a little bit of it, you're making that nucleophile and it pushes the reaction on. All right. What if we looked at alkoxides, our B minus being alkoxy? All right. So we're going to look at an alkoxy group. So the conjugate acid of an alkoxy is an alcohol. All right. Alcohols have pKa values of around 17 to 18, depending on the value of R. All right. So they are effectively just as good as hydroxide. All right. They just have the advantage of making an alcohol rather than water as your conjugate acid. So there are some uses to that. All right. So an example of this would be something like sodium methoxide, all right, or lithium ethoxide, things like that. All right, are examples of these alkoxy groups. All right. Now we can get really serious here and look at something like hydride. All right. So don't get confused. Earlier we were talking about group 13 hydrides. Those are the reducing hydrides. We're going to be looking at group 1 hydrides. All right. So group 1 hydrides are actually basic. All right. So these are like your sodium hydride, potassium hydride. So NaH or KH is what we're going to be talking about here. So group 1 hydrides, what is their conjugate acid? Well, H and H give you H2. All right. So hydrogen is the conjugate acid, and the pKa value of hydrogen is 35. All right. So we've gone up way higher than the pKa value of our ketone. All right. So how much enolate are we going to form here? Well, it turns out it's actually going to be 100%. All right. So we're going to make 100%. So hydride, group 1 hydrides are excellent for making enolates. All right. Another one that is used quite often are called amide bases. All right. So what we have here is a nitrogen with two alkyl groups, and its conjugate acid would be an amine. All right. And these typically have pKa values near 40. All right. So obviously that's going to give us 100% as well. All right. So to recap, if you want to form just a little bit of the enolate, use hydroxide or alkoxide. If you want it to go all the way to the right, slam it to the right, what you're going to use there is either a group 1 hydride or a amide base. All right. So let me give you an example why that would be important. All right. If we want it to be reversible formation of enolate, why would we ever want it to be reversible? Well, this is what we call thermodynamic conditions. In thermodynamics, we like things to be reversible, long reaction times, high temperature, so forth. All right, so having a reversible reaction is good for thermodynamics, because if we get to the wrong product, we can always go back and eventually get to the right product. All right, so reversible formation of enolates, that helps with thermodynamics. You're going to want to take something like sodium hydroxide, right? So what is our enolate going to look like? That, all right? So there's our alpha position, okay? So sodium hydroxide gives us the reversible formation of an enolate. Now, if you want an irreversible formation of enolate, this is better for kinetic conditions. All right? Kinetic conditions, sorry. You're going to want to use a very strong base like the group 1 hydrides or lithium amide. So let's take a look here. So I'm going to use something called LDA. All right? So LDA is, I'm going to say it out loud one time and then we call it LDA forever. Lithium diisopropyl amide. All right? So what that means is we have a nitrogen with isopropyl groups, a negative charge coordinated to a lithium. All right? So that is a lithium amide base. It is very strong. It's like this guy down here. Okay? It's got a conjugate acid with a pKa of 40, so this guy is really strong. All right? So what we're going to see there is enolization in an irreversible format. So once the enolate is formed, it does not go back. All right? So notice the reaction arrows I used. In the case of LDA, I've got a forward arrow that ain't coming back. In the case of sodium hydroxide, I've got a reversible arrow where we can go back and forth between the ketone and the enolate. All right. This was one of our longer videos, so I apologize for that, but I'm going to go ahead and stop here. It's a good point to stop, and then we'll have another video talking more about thermodynamics and kinetics of enolization. Thanks.